go. So we're down to our last couple of weeks. If you look at the schedule, I said we were going to talk about modern physics. And we are indeed going to talk about modern physics. So here we go. It's confession time. Most of what we have taught you is, my notes say incorrect. I'm going to be a little kinder than that. I'm going to say an approximation. It's not really exactly right. Okay? So what we have taught you is called classical physics. Okay? That's what you've learned. Classical physics. And the reason that sort of you can describe what's going on here with a little two-dimensional diagram here, where this is size, right? And here's a meter. And here is a nanometer, 10 to the minus 9 meters. And down here, you can put speed. And here is 0. And here is 1 meter per second. Typical speed, you know. Maybe you could sprint at 10 meters per second. I don't think so. I don't know. You go very fast. But up here is the speed of light. 3 times 10 to the 8 meters per second. So there's all the sizes you can think about. Obviously, if you get bigger. Here's the speeds you can think about. So where do you live on this diagram? You live here. You're about a meter, and you go at about 1 to 10 meters per second. It's the fastest you ever go. And that's where all of classical physics was figured out. Because classical in this case means a long time ago. 14th century, 15th century, 16th century, yada, all the way up to the 19th century. A long time ago when we couldn't think about things or measure things really small, and we couldn't go really fast. But if you leave this area and you start to go fast, suddenly you have relativity. The simple idea that if my longboard is moving at 10 meters per second, and I start walking on it at 15 meters per second, or at 5 meters per second, you would just add those together and say I'm going 15. Well, that's not right. It's actually slightly different than that. Velocities don't just add in that simple way because of the limiting speed of light. It's very complicated. We're not going to get into it. But the formula that you use to do it correctly has this little term in it that at a regular speed is just nothing. It's like a fraction of, a millionth of a percent, so you don't worry about it. If you were to get really small, right, if you were to go down here and go down to sort of the atomic molecular scale, things would get weird, and you would have to think about quantum mechanics. And again, the rules of quantum mechanics, if you start applying them to really big things, basically turn into the rules of classical physics. Okay? And of course, the obvious student question is, what happens if you do both? Oh, quantum field theory, basically, do both. I mean, just the combination of the two. We're not even getting into gravity here. Okay, gravity also had a classical view of what it was, and now it has a more modern view. Okay, so what we're really trying to teach you here, or talk a little bit about, is modern physics. And in physics, modern has the same word, the same meaning as art. It doesn't mean today. It means starting around 1870. Modern art, same thing. Maybe there's postmodern physics. Okay. So, how are we going to do this? Well, we could tell lots of stories about the historical experiments. And it would be like a PBS series. And there could be, I could dress up and reenactments and all kinds of stuff. Because modern physics is based on many experimental observations around 1900. And all these observations were not explainable by classical physics of what people thought was going on. Here's two examples. Thermal radiation. You know how when you heat something up, it glows. If you take the spectrum of that glowing light and try to predict it with simple classical physics, you're not even close. Really wrong ultraviolet frequency. Another one is the lab you're doing, atomic spectra. And you've had some chemistry, you probably know that electrons in atoms and molecules are in discrete states, and when they jump between these states, They emit light or absorb light. That's why we have the lines in atomic spectra. So you probably just accept that now. But it doesn't make any sense in classical physics. But in classical physics, the electron is just orbiting around the nucleus, and it could orbit at any velocity and radius, just like the moon could orbit at any velocity and radius. There's nothing special about a certain one. Well, there is, and that had to be explained. And then there were all these new kinds of mystery radiation showing up, X-rays. What's going on with that? What are X-rays? The speed of light. Had some idea what it was, but its impact on relativity actually didn't come from experiments. This is just because Einstein was so smart. He predicted the experiment that wouldn't make sense maybe in 50 years and went ahead and explained it ahead of time. But that's special, that's Einstein. Technically, this isn't based on an experiment. And then there's also radioactivity. Why do some elements seem to just emit radiation for no reason? That also, there's no classical explanation for that. It wasn't that it was hot. Well, we now use the word hot, even though that's thermal. To say something's emitting a lot of radiation, we say it's hot. So we could go on for a whole semester on telling the stories of these experiments and blah, 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 blah. Also, the names of them also give you a hint that these were experiments that people couldn't explain. Right? Why do we call them X-rays? You know what the hell they were. When X was literally the variable. It's some sort of ray. I will call it an X-ray. Okay? Why do we call something that's radioactive radioactive? It just means it's giving off radiation. We don't know why, we don't know the details, we don't know what kind of radiation it is. It's radioactive. Why do we say it's hot? Well, it's acting like something hot. Is the speed of light truly constant? Yes. Okay. So what we're going to do instead is go back to the reason I rushed us through to get to this point in the first place. And we're going to look at my little study last summer of a certain exam I've been told not to talk about because it gives people hives. Okay? So I'll give you a hint. It starts with an M and it ends in a cat. Here we go. So this was my study of a certain very famous standardized exam you may take someday. And I was looking at what did they ask about and what do we cover in 126? And it was pretty clear they like to ask about some modern physics topics, like radioactive decay and isotopes. 12 questions. How much did we cover last year? 0. Photoelectric effect. 5 questions. How much did we cover last year? 0. We never cover these things. Some of it you get in chemistry, right? I don't know. There's some thermal. You probably do this in chemistry, right? Gen Chem totally covers you with thermal, right? Sure. Atomic structure. Hopefully you get that for chemistry. Probably not much nuclear in chemistry. So that's why we rushed through this year the classical topics to get to modern physics. So now, do I just tell fun stories about, these people and Einstein? No, I'm going to do something real. So what we're going to do, if you look at what I put in the book, in the schedule, it kind of jumps over everything. What we're going to do is we're going to focus on 2 things. We're going to focus on the photoelectric effect and radioactive decay. And then a couple of other, we'll get back to MRI and NMR, things that are kind of interesting that we can write homework problems about. So we're not going to try to do all of modern physics. We're just going to focus on those 2. Because that's what we can write homework problems about. That's what apparently you-know-what cares about, etc. Okay? So I will update the schedule after today to tell you exactly which sections you really want to care about. Because we're going to have time, we're going to do a homework on it, it'll be in the exams, it'll be wonderful. We have time for one more homework to do the last day of class. All right, that's what we're doing. Photoelectric effect and radioactive decay. Anything else we have time for? Today we'll probably the whole time. We'll take the whole lecture to get to the photoelectric effect. Hopefully, because that's all I have to do. But then again, sometimes I run out of notes and I just talk crap and I just ramble and everything and ask a student, did today's lecture make it worse? And they're like, that seems normal. Okay. I guess I'll just stop preparing. Okay. Okay, and the reason I also chose these topics is because they also sort of illustrate a lot of the concepts we've covered all semester. So if we go through these, it's also kind of like review for the exam. Here we go. Okay, so first let's look at the photoelectric section. If you just watch the Khan Academy video, you can understand the photoelectric effect in 6 minutes. But I think if we go through the setup, we'll be able to illustrate a lot of other concepts. Okay? So what it is a couple of metal plates, like this, with vacuum in between them. It's not really that important. You could pretend that there's air in there, but usually you have to evacuate it because we're we're going to have an electron beam jumping around. And you don't want it to run into the air. So you've got a gap, and let's keep it real simple. Let's not even put a battery on it. Let's just make this. This is wire. These are metal plates. Let's just take two metal plates, hook them up in a vacuum chamber with a piece of wire. See what happens. So what I want to start with is to think about an energy diagram of the electrons in these plates. All right? Bear with me here. So remember, I think we've done this once, where we drew a line up and put a U. So that's just the potential energy. The electric potential energy, gravitational, it's mostly electric. There's a little bit of hidden quantum mechanics in this, but you won't have to worry about it too much. Okay? Okay, so we're going to think about the potential energy of the electrons, by the way. Potential energy of the electrons. And we're going to imagine, first we're just going to draw it if we go through the plates. So along this line, say. Just trying to say it's the plates, not the wire. We're going this way, like, through the plates. We don't really care about the wire. Okay, here we go. So I'm going to draw the axis this way. That's like the dotted line there. And we're going to say, well, we know that there's electrons like to sit in the metal, and they don't just fall out of the metal into the vacuum. Why do they stay in the metal? Well, because there's all these positively charged nuclei in here. So, you know, if this thing is neutral, when you take an electron out, suddenly it's not neutral anymore. It's positive, so it sucks the electron back in. So you can pretend that's electrostatics that holds the world together. But whatever, you get the idea. The electrons are sitting here, and there's a barrier to them going into the vacuum. It's really based on atomic structure and everything, or electronic structure, but let's just pretend it looks like this. So there's a barrier here, an energetic barrier, like that, all right? And then in the metal, so this is the metal, this is the gap, and this is the metal. And we often like to think about how the electrons kind of fill up. You know, we have an electron here in the metal. We have another one here, another one here, another one, another one on top of that. And they build up higher and higher energy. We can pretend it's because of electrostatic repulsion, I guess. But really, it's just the electrons fill up all these energy levels. They're all this energy. And they make kind of like, you can think of it as like a little liquid. So rather than draw thousands of dots, I'll just kind of draw it like that. So these are the electrons sitting in the metal. And that makes sense that they're down here, and the energy they need to get to the vacuum is up here. That's why they don't just fall into the vacuum. It's like if I dug a hole and put a ball in the hole, the ball's not just going to jump out and be on the ground again. It's stuck in the hole. It's stuck down here. On this side, same thing. You got a bunch of electrons down there. So in the real world, the electrons just jump into the vacuum and go across? No. There's no reason they would do that. They're stuck in the metal, they can't get in the gap. And in this diagram, they're stuck in the metal, can't get in the gap. We're going to start that simple. Okay? Now, let's add a battery. That's the first thing we need to the photoelectric effect is add battery. Okay, review time. What is the battery going to look like? What symbol do we use for the battery? It's going to come along like this. Can you find the battery in that picture? I hope so. Okay, the battery is the symbol. And remember, the long line means the positive side. We probably wouldn't make you know that, but just there you go. I'll draw it for you. Positive side. What else do you know? Well, you know this wire is touching a piece of metal and everything, electrostatic, so this thing is also positive. So we have a positive plate and a negative plate like that. Still no current, because this is like a massive resistor here. The vacuum gap is like R equals infinity. This also looks kind of like a capacitor, doesn't it? It's two plates with nothing in between. Current doesn't flow. It's kind of like a capacitor. I think your mic is off. Also, the lectures from last week will be posted. The lectures from last week will be posted eventually. My mic is on. Yeah. Let me talk louder! Yeah, I'm just having trouble with the files, and I wrote through proposals last week, so they'll be up there. Definitely in time to study them for the final and the demo. Yeah, I thought. Okay, so now let's draw this diagram. Okay, be thinking in your head, what would change about this diagram? In which way would it change? While I'm sitting here rambling, you be thinking. That's how this class works. Here's the energy of the electron. Here is sort of position. And again, we're going through, we're going through the plates. Okay? So what is going to happen when you put these at a higher electrostatic, or sorry, this side at a higher electrostatic potential than that side? You're basically changing the energy of the charges. Remember, because you remember that we're applying a delta V here. And remember that the energy is Q times delta V. So the difference in energy between the two is Q times delta V. So you're going to say that the electrons on one side are higher energy than the other. But the electrons are negative. Okay? So this side has the higher potential of the delta V, but this side has the higher energy for electrons because electrons are negative. So that negative flips it. Higher potential, higher electric potential, but higher electron energy. And also just electrostatically think about it. Is it going to take more energy? Am I going to have to do work to force the electrons onto this plate or let them flow onto that plate? You have to do work to force them onto here. This is a negative plate. They don't want to go there. So the way you would draw it is you'd say, okay, then this plate is down here. Now this plate is up higher like this. There's your two plates. Interesting. Now, could we also think about how the gap is different? What now exists in this gap? There is now an electric field in that gap. Right? Parallel plates, this one's at, 0 volts, say, this one's at plus V volts. You're going to have an electric field like that in the gap. And in the electric field, what changes uniformly as you go down the field? The potential. So we should have the case that the potential is varying through this gap, and sure enough, that's what we have. I'm going to draw it, exaggerate it, I'm going to have it come down like that. There you go. Now you might say that's going the wrong way. The potential goes down from high to low, but remember, this isn't the electric potential I'm plotting, this is the energy of the electrons. That's why I have it going down this way. Electrons are at higher energy here, and lower energy there. So this is what we've done to this system. So now we can also still draw the electrons on there. Here's all the electrons filling up all these levels here. Here's all the electrons filling up all these levels here. Okay. Now in the real world, is this going to make current flow across that gap? No. Right? Capacitor, there's still infinite resistance here. Current's going to be V equals IR, V divided by infinity is 0. There's no current. In this diagram, there's still no current. Right? Just because we lifted this one up and tilted it a little bit, the electrons still can't get over that barrier. Right? They're still stuck right here. There's nowhere for them to go. Okay? We'd have to have the barrier be gone to fall from one side to the other. So there, we haven't done the photoelectric effect yet. We've already talked about multiple concepts from the class. So let me put a couple of notes on here so it makes it clear. Is the increase in potential energy linear? This is linear if these were closely spaced plates. Right? These were like large, closely spaced plates. It's like infinite gap or an infinite sized gap. That means the field would be uniform. If the field is uniform, this would be linear. The way I've drawn it, it's not really, it would be linear. It's more like two charges marked each other. But yeah. But usually every problem we do, we'll say, I drew it this way, but pretend it's two big plates with a small gap. Okay. So here, we say they stay in here. So, okay, but the one thing we want to add is, so electrons, that's the symbol for electrons, by the way. Still, that's my symbol. I think it's the general symbol, an E with a negative sign. Are still stuck in the metal. But what's different then about these two is, if one got over the barrier, it would flow down the barrier. If it would get current, one got into the gap, you'd have current flow, wouldn't you? Right? You wouldn't get current flow because if just one electron can somehow magically hop up here, then it's going to go down here. And you'll get current flow. Which way would the current flow be? Same question. Electrons this way, you'd have current flow that way. Along the electric field position. So the negative plate is the straight line on the right of the graph. The negative plate is here, and it's represented by this. And this is the positive. That's like here. I was saying this is the negative plate. There's the gap. Here I didn't quite align them perfectly. Actually, I did. Just perfect. Okay. So So now, we're going to do some experiments. We're going to do some Gedanken experiments, which is like German for thought experiment. Where this is like what theorists, when they do experiments, they don't really do them, they think about them, and they always work the way they want. So it's really great to be a theorist. So here's Gedanken experiment 1. You know what it's called when you do a thought experiment without doing a thought experiment? It's called a Gedanken. That's the technical phrase. Okay, experiment 1. We're going to shine light waves on the negative plate. Shine light waves on the negative plate and see what happens. Oh, well, it's a Gedanken experiment. We don't have to do it. Let's just say, oh, I know what's going to happen. Current is going to flow. Current flows proportional to light intensity. Current flow. Why would that happen? Let's draw it real quick. So now we got our 2 plates. Here they are. Beautiful. We have the best plates. And we're going to put like some of this on here, like a battery there. Yeah. And now we're going to send in what? Light waves. Ah. Yes. Let's do it how you guys would do it. Oh, I got the camera out. Yeah. Here, I'll draw a phone shining the light waves just to make it, I'm trying to be relatable. There we go. Phone shines light waves onto the electrode. Now what happens? As we said, we get a current flow proportional to intensity, which pains me. It pains me to call it intensity. Okay? It should be a radiance, but I'm going to match the book and use the old-fashioned incorrect word. Okay? We shine the light on it, suddenly we get a current. And it's proportional to the light intensity. And so we can ask why. Well, let's draw our little diagram for this and see what's going on. I can't draw it underneath because I spazzed and made this too big. So I'm going to draw it over here. Here we go. So here, we said we had these 2 at different heights here, like that. We said we had a gap like that. None of that has changed. We have some electrons here, and we have some electrons here. Like that. Nothing's changed. But then the light is basically knocking electrons over the gap. And then they fall down. Okay, so put a note on that. Light. Now we can use several words here. Depends on if we are, classical or what. Well, let's not explain it here. I have a quote from the classical physicist on the box. So here comes the explanation. Why is current sometimes I and sometimes I? It's always I. The question makes no sense. This class is not case sensitive. Yes. No, I try to write when the current is changing in time, use little I. When it's constant, use big I. But I forget all the time. Sorry. Suck at this job. Okay, so you shine light on this electrode, it pops electrons up. Here we go. So the classical physicists, now we're going to say, what does the classical physicist say? What does classical physics claim is going on here? And that's how we're going to see if these new experiments, like the photoelectric effect, make sense. Okay? Okay, so classical says light waves are basically energy. They're a way to transport energy. They heat the electrons. Heat electrons and push some over the barrier. Push some over the barrier. Over the barrier. Right. And they therefore create current. So that's fine. Right. And everything makes sense. If you have no intensity, no light. So intensity in this whole lecture means the amount of the light, the brightness of the light, the power of the light. So if you have no light, you get no current. You add more light, you get more current. That seems okay. The whole story holds together. So we have no problem with that. Let's see if we can let's find the problem. Sure we can. Let's look at another experiment. So classical physics happened. let's look at experiment number 2. Gedanken experiment number 2. Is it even possible to heat electrons? They're already moving so fast. How fast are they moving? You don't know how fast they're moving. Don't give me that. Okay, experiment 2. The drift velocity in a metal wire conducting currents like a few centimeters a second. I think they go faster than that. Experiment 2. I'm sorry, I'm being mean today. I forgot the question. Yes, they can always go faster. They're not going so close to the speed of light in the metal bouncing around that they can't go faster, so they can go faster. But really, the idea that they're moving in the metal is a classical concept that's wrong anyway. So that's why we don't worry about thinking about their exact speed. That's what we're getting to. Okay, some clever person came up with experiment 2. What about this? Experiment 2 says that there is no time. So somebody said, let's put a shutter on this light intensity. Let's use a shutter and just turn it on suddenly at a certain time. No light, no light, no light, no light, nothing be light, boom. Sorry, I got a little megalomaniac there for a minute. And let's look at the current. Just for a minute. Just for now, no current, no current, no current, no current, no current, no current, and boom, current, immediately. So it seems like it heated up those electrons pretty fast, which doesn't seem right. It seems like it should take a little bit of time to heat up the electrons. You can say, well, maybe the electrons don't have much of a heat capacity, and it's pretty easy to heat them up. Don't mess with my story. Okay? It should take some time to heat up the electrons. So the classical physicist says, uh-oh, we're in trouble. It should take time to heat the electrons. And you can say, no, it shouldn't. But what I can do is I can turn this way down. We can turn the intensity limiting down to 0 and still get a teeny current. So a differentially small intensity, differentially small current. With that teeny intensity, it should take a while to heat these things up. It's immediate. Even if you barely turn the intensity on, you immediately get a teeny current, especially at low intensity. TF, which means where is the filibuster? There should be a delay. Why is there no delay? So the classical physicists can't really explain that. They don't know why there's no delay. Now, do we have to completely rewrite physics over that one little missing delay? No. Let's see. Maybe if there's other problems, we need to completely rewrite physics. Let's look for some others. Maybe you can think of it. That was experiment 2. A little bit of a problem. Let's look at experiment 3. Experiment 3. Okay, this is the big one. All right. This one's really gonna be bothered. If you feel classical, this one's gonna bother you. Current requires a minimum frequency of light, regardless, I shouldn't put irregardless of intensity. I don't think that's a word. Okay. So now, next experiment, let's plot the current you get versus the frequency of the light you shine on. All right? So no time dependence. Let's just say I've got my little monochrome, I've got a little tunable light source. And I started with red frequencies, and I start turning it up. Remember, frequency is inverse of wavelength, so this is red and this is blue. Turn it up, turn it up, turn it up. Nothing, nothing. Suddenly, there it is. Right? It's F naught. So to get any current at all requires a minimum frequency of light. Okay? And to make matters weirder, F naught depends on the metal. clearly has something to do with the metal, the fact that it needs some minimum F naught. Well, that's weird. Let's see if a classical guy can explain that. All right. So light is an oscillating E field, is what classical physics thinks. An oscillating E field that pushes electrons and heat them. Heat them at any frequency. It shouldn't really matter. You could do it at 1 hertz. It's going to push the electrons. You could do it at 100 hertz. You could do it at 10 to the 15 hertz. It shouldn't really matter what the frequency is. Eventually, you should be able to heat them up. Now you could say at low frequency, maybe it doesn't heat them up enough, but it's also independent of intensity. If you're at low frequency, just turn it up, and you never get any current if you're below F0. And it's also, this is sharp. This is like a 1% change, and you go from no current to lots of current. So it's not some phenomenological difference between like radar waves and light waves and X-rays. It's a change of just 1%. Suddenly it turns on. So there's something clearly very special going on at F0. So it should happen at any frequency. Classical guy is mad. WTF, why the F0 is what they would say back then. Why on earth does it matter? That's only experiment 3. Oh, let's do experiment 4. Oh, experiment 4 is very complicated. No, we'll set it up in the first half. Slam it home in the second half. Build some tension, ruin the break. So this isn't the break, that's what we're going to finish it, nibble on the break. Which will be so curious how this works. You won't be able to enjoy the break. Experiment 4! Here we go. I'm getting excited. Very. We haven't thought about this yet. The applied delta V. Yes, get a different battery. Oh, it's 1870, there's only one kind of battery. I don't care, get a cat. We're going to vary delta V. Okay? And we're going to see what happens. Here's the plot of what will happen. So there's the current, and here's delta V. Putting it on both sides of the origin. Okay. So the way we described it is this side. You know, you apply the cathode, you have one of the words. The negative one is the cathode, you make it negative, and you shine a light on it, and you're over here somewhere, and it looks like that. Now we're going to vary the battery and see what happens. If you vary it up, if you apply more voltage in the way we've been applying the voltage, it basically saturates. If you go down, you still get it, even when you have the voltage the wrong way. So sort of our diagram said, okay, you put the voltage this way, you apply the light, and some of them hop over the barrier and give you current. If you apply them the other way, you actually can still get current. What's happening is you can give them more energy than just barely enough to get over the barrier. Right? So you could have this tilted the other way and the light just knocks it all the way over the barrier. Okay? So you actually can get current on this side. We just draw that one back. That one's higher. So the light comes in and says, boom! All the way over there. Okay, so it can happen. Even though we have negative delta V, it can still happen. Okay, so that's not the mystery that it can still happen. So we got to think about both sides. We got to think, what's going on here? Why is it saturating? And what's going on here? Why does it have this minimum voltage? So let's do the right side first. That's easy. So the right side, we all agree. So the current saturates at large delta V as the field catches all the current, as the field catches all the electrons. All of the electrons. This is like like an experimental artifact. Right? All this is saying, yeah, I increase some electrons, and some of them miss. Some of them go straight over, some of them fly off this way, and they miss. As you crank up the voltage, you get more larger and larger field with bigger forces, you eventually suck them all. So nothing real enlightening there. Although I did write a comment from the classical physicist. Oh no, that's on the other side. Okay, so everybody's happy here. Okay? Nothing too weird. This is called the stopping potential. V stop. And it's basically saying, eventually, if you turn this up enough, they won't get over anymore. And eventually you won't be able to make it. Okay? The light can give them enough energy to get somewhat over the barrier, but they can't get all the way. So reversing delta V still allows current up to the stopping potential. Potential. And that seems okay. There's nothing inherently bad about that. You could even explain that classically. Right? If the light is strong enough, it gives it enough energy, it can knock it over a barrier. Eventually, the light can't give it enough energy to knock it over the barrier. Right? So the classical guy would say, sure, this is fine. And if I hit it harder, if I increase the intensity, this is low intensity. What would the classical guy say? If I increase the intensity, I should get more. That's true. And therefore, the stopping voltage should go this way. If I give it more energy, it could get over a higher stopping barrier, right? Well, guess what happens? Oh, no, it starts to fall. It goes to the same stopping potential. It doesn't care what the intensity is. Intensity to the same stopping potential. How's the diagram on the left different from experiment 1? They're all experiment 1. They're all shining light. They're all doing this. How's it different from this? So yeah, the difference is we've switched the battery. So here we're on the negative side of delta V. We've actually turned the battery around. Okay? So now if it's a power supply, we'd switch it to negative, or if it's a battery, we'd switch the battery. So we actually have the positive side here and the negative side here. It still has electrons in it. You can still knock them out. You can knock them with so much energy, you can shoot them over this barrier. That's what we're doing. But what's amazing is turning up the light doesn't get more over the barrier. Right? It's still, that barrier will stop everything, no matter how bright the light is. Okay, so the last thing we're doing. So the classical guy is really flustered now. Okay, but why is V stop the same for all intensity? He can't explain it. Higher intensity should be more energy into the electrons. They should be able to go over a higher barrier. It should have come back here. So this is the last one. Oh, he's fun. Which is why that is. Why is the V stop stuck right there? Why can't it vary? Okay? So as you can imagine, people were quite upset. In bars, coffee houses, all over the world, everybody was talking about the photoelectric effect and what's going on. Okay, so clearly classical can't explain these observations, so we'll explain it in a second. And we'll do a problem. What's the sign of V stop? V stop is a magnitude. You put it on the negative side, you apply the negative potential, but V stop itself, the number is always given as a magnitude. It's never given a negative sign. just to answer your question, keep talking. Just answer it. Yeah, I'm going to update the schedule. Yeah, I can't remember. Get through this. I got some good questions here. We want to be sure this is all clear. You'll see when we do the questions at the end, the way we can ask questions about this. Okay. What does it mean to reverse delta V? So just a quick reminder. So if you understood, you don't need to draw this, but if you don't know what I meant by reverse delta V, I'm about to do it. Here we go. This is the first diagram. This is a battery, positive, negative. This is electron energy, right? So that's why it's higher energy on the negative electrode, because it's the energy of an electron, it's not the potential. The electric potential, of course, is higher here and lower there. The electron energy, higher here, lower there. Looks like that. By reverse the battery, I literally mean take the battery out and stick it in this way. That's what I mean by reverse the battery. Literally flip it around. The diagram says to put the bump on this side. Don't put the bump on the other side. Be crazy. Come on. We can do this. Oh, what's that going to do? So what that's going to do is it's going to change the diagram where it's just going to flip the diagram. That's what it meant. And you say, how can an electron possibly now go this way? And it can, because the light is giving it the energy to jump all the way over that barrier. That's all it's at. Does it push against the battery? Yeah, it does. How can? Well, the light's acting like a battery. The light is like its own little electromotive force that's going to overcome the battery. Think of that. Don't think of the circuit too detailed, or it's not worth it. Okay, that's what it means to reverse delta V. Well, the final will be fully cumulative, or will focus mainly on stuff from these units. It will be cumulative, maybe a quarter on the first section, a quarter on the second section, and a half on the third section. Right now, that's an approximation. That's a classical approximation to the written exam. If you thought about the exam. But obviously, we will tell you more as the exam approaches. As we plan it out, we will tell you. But it will be at some level cumulative for sure. Why is the plot for experiment 4 linear on the right? So this was the explanation for the right side, this is the explanation for the left side. So it's linear because the current saturates at large delta V. right? A certain amount of light is only going to generate so many electrons. And they might hit and they might miss as they fly across, right? You bring in the line, some of them are going to hit, sure, but some of them, this one might get kicked that way. And it'll go, woo, and you never see it again. But if you crank up delta V, you make the field bigger, and therefore the force is bigger, it'll start like this, but the plate will say, no, you got to come this way. So eventually you catch all the electrons. And then there's no more electrons to catch. So that's what I meant when I said this is an experimental artifact. It's not really relevant to the physics. Right? It's really the fact that we're coming to the same point. That's the physically important point. Where did you first mention reverse delta V? I don't know. Ask the person who asked about reversing delta V when I first mentioned it. I don't know. I've erased the board right yourselves. Go back to the videotape. This could be like, NFL replays. There's where he mentioned delta V. He had to find it again. Flag, 10 yards, 10 extra points for everyone. All right. Okay, so now we're going to see who figured this out. Oh, well, guess. Mr. Hunter Boy. No, I wasn't alive. God, born in 71. Einstein's view, the modern era was over. It was Einstein. He figured it out. Okay? So we all think of Einstein with relativity. And relativity was a pretty amazing discovery, considering he had to gedonk the whole thing before anybody had measured it. But he actually had the Nobel Prize for this. He explained the photoelectric effect, not relativity. So here's what it was. There were people at the time thinking that energy levels might not be continuous. They might be discrete. So the idea was out there. He said, I've heard, we're going into the historical, sorry, I've heard energy levels are discrete. And I got to spell discrete right. It's really embarrassing. I think I want to spell it E-T-E. Yeah. Are discrete, and light is energy. So light is a particle. There had actually been a debate going on for years: is light a particle or a wave? Most evidence at the time made it pretty clear it was a wave. You yourself have seen it do double slit diffraction or interference. We told you the whole first third of the class that light's a wave that can spread out and interfere, but actually no, light is a particle. This is the experiment that pushed the idea that light is a particle. Okay? So now let's draw this experiment as Einstein visualized it here. So it's got the battery. He put it in the right way because he got somebody to help him here. And it goes like this. There you go. So Einstein says it's not little wavy waves that are distributed in space hitting the thing. It's particles ramming into the surface. Particles of light called photons. Like that. And the particle hits a single electron. And the electron flies out. Photons fly in. The symbol, if you might ever see it this way, is a gamma. You draw a gamma for photons and the little E minus for electrons. Okay? So, let's look at the bullet points that Einstein laid out. He used bullet points. That's where I got that. Photons knock out electrons. Here's the key phrase. Photons knock out electrons on a one-to-one. Oh, this is so important. I'm going to give it its own line. On a one-to-one basis. That's really the entire idea that explains the photoelectric effect. It's not like a wave that's slowly heating things up. Instead of photon, like a billiard ball, just knocks the electron out. As soon as you accept that, the whole photoelectric effect makes sense. We're going to go through it. That's the fundamental difference. So then we got to reformulate the properties of light. So what does higher intensity mean? Higher intensity means more photons. Right? It's like water molecules. It's just a stream of photons. So more intensity just means more of them per unit area, per unit time. And then this is the big one. If it's a particle, particles have energy. Okay? Waves have energy. They have sort of, since they're distributed in space, they have like their intensity is their energy per unit area. But for a particle like a photon, all that energy is in one little particle. So we can't calculate it the same way. We can't say the energy per unit area of a plane wave. We need a new formula. So photon energy is this. Photon energy is E equals H F for frequency. Okay? So you know what E is. E is energy in joules. know what F is, I'm going to tell you here. It's frequency in hertz. That's F. Right. But H is, of course, the famous thing from quantum mechanics, Planck's constant. Or Planck's constant, if you're being fancy. And it is a very small number, 6.626, I forget, 6.63. 3 times 10 to the minus 34 joule seconds. 6.63 times 10 to the minus 34 joule seconds. So when you multiply it by frequency, hertz is 1 over second, so that turns it into energy. So the units work out. That's the energy of an individual photon. So it's not surprising it's a very small unit. Because a single photon doesn't have a whole lot of energy. When you look at light streaming down, you're looking at billions and billions and billions of photons. Not individuals. Well, your eye can almost detect a single photon. I think your eye can detect like 10 photons, like a burst of about 10 photons. Okay, so that's the fundamental difference. Now let's look at how does that explain all these experiments. We'll just do a little bit, a quick sentence on each one. And then we'll look at a little bit of the math Einstein did. And then we'll look at a practice problem. Let's see. So let's look at it. See if this makes sense. Experiment 1. Experiment 1 makes sense with photons. More photons, more electrons. Sure. More photons, more electrons. Of course, that one was also explained classically as well. Pretty happy with that, experiment 1. Experiment 2, that was one that was not explained classically. Experiment 2 was the lack of a time delay. Because a wave needed a little time to build up the energy, because the wave is sort of evenly putting the energy in all the different electrons. They're all slowly getting some energy from the wave. But that's not how it works with photons. Right? The first photon to arrive might knock out one another. Might knock out. The point is, because of the fundamental difference, the one-to-one basis, because it's one-to-one, it's not a distributed energy, there's no need to wait. There's no heating going on. Like an electron, no wave heating. Right, that was the classical idea that had the problem. Experiment 3. Why do we need a minimum energy? Remember there was a minimum frequency. Well, now it's maybe clear is that the photon, since it's now one-to-one on particle, one particle on particle, photon needs to give the electron minimum energy to get over the barrier. Classically, you'd say the wave can eventually give it enough energy, even if it's a really low frequency wave, should be able to heat it up, and if you give it maybe an hour, eventually it won't get knocked over. And that's not how it works. Right? It's all just the amount of energy of a photon going directly to one electron at a time. The photon doesn't give it enough to get over the barrier that I've sort of erased here. If the photon doesn't have that much energy, it's not going to make it in this case. Or if the photon doesn't have that much energy, it's not going to make it. And the energy is directly related to the frequency. The reason for the minimum frequency is it's really talking about the energy. Will we have another pledge problem? I'm glad you're really following along. Yes, another pledge problem is coming out very soon. On, I don't know, Faraday's law or something like that. Does one photon knock out one electron, or can it be more? In the energy regime we're talking about, it's basically one-to-one. We're sending in light with an energy about the same as this barrier. Visible light, the barriers are about the same. If you send in a gamma ray, sure, it can knock out all kinds of electrons. Okay? There's a reason all these energies are about the same. That's like why chemistry exists and why our eyes see these energies. Because that's where all the matter interactions are about the same scale. That's why we don't have eyes in the X-ray. There's no chemical bonds that work well with the X-ray. But no, a high energy photon could knock out more than one electron. Experiment 4 is the more confusing one, this whole stoppage thing. That's where all the interesting math is, so we got to talk about it. So why was it that no matter what you do with the intensity, V stop is the same. Let me write it real quick. Is because V stop depends on the energy. V stop depends on the electron energy. On the electron energy, which does not depend on intensity. Which does not depend on intensity. In the wave view, you would say, well, more intensity means I'm dumping more energy over time, because waves are distributed and they're talking to all the electrons. Therefore, this should have been farther over. But no, it doesn't matter the intensity. Every photon dumps the same amount of energy in individual electrons. And if that photon has a certain amount of energy, this is the highest it's going to get over the barrier. And this is basically just making the barrier by adjusting what the V stop is telling. So V stop is on the electron energy, which is not on the intensity. It depends on the frequency. So you can see the photon picture basically explains everything, all 4 experiments. This is why people believe it does. So because of Einstein's view, we can explain all the experiments as a result of photon interactions, a result of photon-electron interactions, one-on-one. Don't worry about the multiple electrons. Is the direction of the current created something important to consider? Yes, because that's an easy little question we can ask you. Which way is the current? It's the opposite direction of the electrons moving. That's like just a total obvious, or not obvious, but it's like something we're definitely asked. Test that idea that current is the opposite direction of the electron. So light is not a wave, or light is not always a wave? Oh, that's the quantum mechanics class. We don't have time for that. So light is a particle that exhibits a wave-like nature, is what you can say. When it was first being figured out, somebody tried to coin the phrase wavicle. That was like, tried to catch on. And then in the 90s, I tried to bring it back at Trinity. I had everybody saying wavicle, but it didn't quite catch on. It came very close. But basically, it's not really a wave or a particle. It describes like a wave function, blah, blah, blah. But really, if I had to pick one or the other, I would say it's a particle. I mean, it is a particle. It just has a wave-like nature to it. I can ramble a whole quantum mechanics course for the next 10 minutes. It wouldn't be very good. So if you really want to know, well, I'll save that for you. Oh dear. Okay, so now we're going to look at, so if Einstein just says this, I mean, this is 1905. He's not Einstein. He's just this patent clerk that started writing papers, right? So if people just immediately fall down and say, oh, that's a particle, you're a genius. No, that's not how it works. How do you know which side the metal gets electrons excited by? So in all these things, the light is shining on the right side. That's just how I drew it. You could shine it on the left side. If V depends on electron energy, is independent of intensity, how do higher intensities give a higher current for the same V? Because higher intensities have more photons. The intensity of a light beam tells you the number of photons. So more photons, more electrons. Okay, so people just didn't fall down and say, Einstein, you're a genius. He had to make a prediction. Right? So let's look at the prediction he made based on this model that light is photons. So let's look, just now we're going to kind of, we're going to zoom in here on, I drew it backwards. Let me draw it the same way here. My notes backwards. Metal. Vacuum. Now we're going to zoom in on that interface. And what happens when we shine light on it? Okay? Oh, I need to draw bigger. It's really big. All right. Metal. Vacuum. And now, if you really want to be a wave-particle duality, you draw the light like that. It's a little wavy thing that's localized with an arrow on it. Okay? So there's that makes you feel better. How we just call it. So photons are shining on the metal. What's going to happen? So let's draw our energy diagram. Again, this is the energy of the electrons versus position. So we say they like to sit down here in the metal. Lower, they like to sit down here in the metal, and there's a big barrier to getting up to the vacuum. So this is vacuum, this is metal. Here's all your electrons sitting down here in this energy well. They're trapped there by the chemistry. Can't get out. So let's start labeling things. So the difference between the top of where the electrons are and the vacuum level, I'm going to call E naught, energy naught. Okay, so E naught, because so we're actually going to do some math and problems. We have to start writing some equations. So far we have one equation, E equals HF, wherever it was. the energy of a photon. So we need more. Okay. So E naught has a name. It's called the work function. Okay. And you can see what it is. It's basically the minimum energy you need to remove an electron, or it's the energy gap between the highest energy electron and the vacuum. So usually in these problems you go with that minimum definition. The minimum E to remove an electron. Okay? But I think the best way to describe it is just to look at this diagram. You should be able to reinterpret this diagram. This electron needs a bunch of energy to get to the vacuum level. This is just how much. And also it's interesting, it depends on the metal. Different metals have a different work function. And that's a very fundamental concept if you decide to go into solid state physics. Could happen. I'm going to define something that's not in the book just as like a mathematical patsy here. Okay? I'm going to call it ED, is the how deep in energy is the electron the photon hits. How deep in energy is the electron the photon hits. In some descriptions of the photoelectric effect, they say you always get the one at the top. They don't worry about what if one of these came out. We'll be the book kind of does both. Right? So I'll say it's possible that the photon will come all the way down to here, knock this electron out. So that's what I would call the ED, the depth below the work function, not all the way from the vacuum. Okay? So just know it by the diagram. We're going to divide it out. Is there a range of potential energy in the electrons that you have? Yeah, the shaded region basically means some of them can be here, but some of them can be farther down. So that's why we often talk about the minimum energy to remove an electron. We're talking about the ones at the top. And you can see that by this definition of E naught. It only goes to the top level. These are further down in energy. I'm saying the photon could knock those out. There's the photon. Comes in, knocks the electron out. So E deep is how deep in energy it hits. So now all we're going to do is conserve energy. Right? That's not so bad. Let's conserve energy. Of all the classical physics concepts we told you, a few of them are true. Conservation of energy is not one. Well, let's do it anyway. Let's see. So what's the because mass energy are the same thing. We have conservation of mass energy. They can interconvert into each other. Conservation of momentum is the one thing we told you that is absolutely true. Everything else, Okay, so let's conserve energy. Let's see. The energy we're putting in is the energy of the photon, HF. That's how much energy we're going to dump in this system. Then the photon basically, it disappears. Let's not worry about it. When it gives up its energy, it winks out of existence, let's say. So all that energy goes into the electron. So what is the change of energy of the electron? Well, it's going to go up here, and it doesn't even have to just get here. It could go to here. Right? So here's the electron now, in this diagram. So it also has kinetic energy. Right? If it's given more energy than how deep it is, plus the work function, that excess is just going to make it move faster. So that's kinetic. So the HF, you can see from that diagram, is how deep it was when it got hit, plus the work function, because of how I described the depth. I described the depth from the work function. So you got to get this much energy, plus this much energy, plus however much kinetic energy it gets in. Just conservation of energy, nothing crazy there. Just adding those freely. We're not even describing them fundamentally. Just wrong. Okay. Now, just got a couple more bullets here, and then we'll see more. Okay, so now I'm going to do what a lot of other derivations do, where they say all the energy comes from electrons near the work function. They don't really come from that deep. So let's say the typical approximation is most the electrons come from the top. Okay, so ED equals 0. I want to go for that sort of descriptive version. Hopefully you know what I mean. The top means most of them you're getting from right here. So really there is no ED here. getting them from a depth equal to the work function. So if we say that's true, then we say HF equals 0 plus the work function plus the kinetic energy. Okay. So we blow them out. We wrote that equation. We're in good shape. Okay. So now we're going to relate this to the stopping potential. This is related to the stopping potential. Here we go. All right, this is the key. Stopping potential basically removes kinetic energy. Okay, that's the whole idea. So if we have the thing backwards, here's the diagram. Yeah, so we have the, remember this is where we bias it the other way. So it gets up its E naught, work function, and then whatever kinetic energy it has, once it has just that much, you'll still get the current. Once the kinetic energy goes down below that stopping potential, it doesn't get there anymore. That's how you tie it to this. Right, so if we draw that again, just so you can see it a little more clearly, we biased it backwards, like that. We kick one out. If you kick it out this high, it makes it over. Kick it out this high, it doesn't. So whether or not it makes it out depends if that K is equal to that. Is that kinetic energy equal to the stopping potential? That really just defines whether it gets out or not. Okay? So the way you would write that in terms of an equation is you would say V stop is the maximum kinetic energy they're getting. Okay? What's the most we're getting? Well, the most we're getting is basically that. V stop is that. So now if we want to write V stop in terms of these values, you just say, oh, sorry, this was a max. Okay, so when you get an electron from the top, that's the most kinetic energy you're going to get. That's what I was trying to say. So here, you know, if you get one from down here, you don't get as much kinetic energy, right? The whole thing's lower. If you get one from the top, you get all the kinetic energy you're going to get. So that was supposed to be K max, the maximum kinetic energy, and then the V stop stops it. And you say, wait a minute, this is potential, electric potential, this is energy, so you put an E on here. We're talking about individual electrons. Okay, we're going to bring this home in the final minutes, or I meant to be able to wax on it longer. Wax, that means like discuss it. Equals HF minus the work function. See, all I did was I solved this for K max and said it's how much energy you put in minus the work function is how much kinetic energy you have. So set that equal to E, the charge times V stop. Okay. And then we rearrange a little bit and say, well, is we bring this around here. Oh, no boards. So I'm blowing it at the left side. We're going to solve that for V stop. We're going to say V stop equals what? We're going to bring the E under. We're going to leave the H on top. H over E, which is going to make it F minus, but now we have this E naught. Okay? We have this work function term, but that's the origin of F naught. Right? If you turn the frequency down, eventually you reach the minimum frequency where you'll get an electron out. That's the work function. If you divide it by E. Right? So that energy divided by E is like the F naught. Right? If you do the H and the E on it. So sorry, I didn't have time to do that for you. Okay? But this is related to work function. If you think back to the second or the third experiment. So Einstein said, so nobody had done this experiment. Nobody had tuned the frequency and measured F naught. Okay? Oh, yeah, or sorry, nobody had sort of tuned the frequency and seen how did V stop depend on the frequency. So Einstein said somebody should do that experiment. And somebody did it. Robert Millikan did it. Okay, so he did this. He said, what is V stop versus frequency? And sure enough, he got something like that, which had F naught there. It was a line. What is the slope of the line equal to? H over E. Two fundamental constants of the universe. Who measured the charge of the electron? Millikan. Right? So Millikan says, oh, I've just measured Planck's constant with Einstein's new suggested experiment, and it matched the other measurement of Planck's constant. So then they said, okay, two independent measurements measured Planck's constant, got the same number. This must all be real. So maybe we should make a stamp about Einstein. Maybe he does get a stamp. Okay, so I'm going to write homeworks on this to let you know what we want to ask. I had 5 MCAT questions on it to show. We didn't have time. I will post them. I'm not going to post the entire MCAT because I paid for it and signed this thing to go to that. But I'll show you these to give you an idea of what their questions are. Very touchy-feely, takes it back to circuits, and ours will be more calculate a few properties. But I'll give you an idea of what you need to know. Almost done.
And like, there's one in class, you can't get in your room. Yeah, it's not in the phone. Wait.